Thank you very much for attending my talk. So I'm Haixu Tang from Luddy School at Indiana University, Bloomington. So I'm going to present deep metric learning for improving peptide identification in proteomics today. So this is mostly done by actually PhD student Kai-Yuan Liu. He, for visa issues, he cannot attend the meeting. So I'm going to present work. So as you have heard from many talks in this section, so peptide identification is a critical or the key problem in bottom-up proteomics. Briefly, in bottom-up proteomics, a protein mixture was a complex protein mixture was first digested by protease like a trypsin to cut the protein into peptides, and then peptides are subject to LC-MS analysis, resulting millions of tandem mass spectra, which are used to identify the protein. So as the 20 years progress of proteomics, many peptide search engines has been developed, including many famous software like many of you are using. The key issue here for those peptide search engine is to determine a peptide spectral matching is true or false. Essentially, you try to identify the peptide based on the PSMs. As you have heard from the talk in the morning, especially by Varun's talk, a lot of work has been done to develop different matching scores to distinguish true and false PSMs. In fact, not only those scoring are used in the peptide search engines, they're also post-processing scoring schemes, as you heard from Varun's talk, to develop to distinguish the true and false PSMs. Like Varun proposed to use a scoring based on de novo algorithm, Casanova. But there are also other approaches previously, like a probabilistic approach, machine learning approach, and more recently, deep learning approach, trying to score the matching between the peptide and the spectral to tell which PSM are true and which are false. And afterwards, you can also, based on the scoring to distinguish them, to also control the false discovery using a target decoy search approach, as you have heard from the other talks as well. I want to mention there's another approach that was not used very often, but also showing promising results. Instead of searching a peptide database, it's proposed to search against spectral library, which is a collection of previously characterized spectra from peptides, and has been showing that to score, as you can intuitively see, the scoring of two experiment spectra, it should be easier than score a peptide and a spectra in the PSM, because essentially you have to develop empirical rules to define how to matching a peptide and experiment spectra. But to score two experiment spectra should be straightforward. For example, you can just use cosine similarity to compute the similarity between two experiment spectra, because they are supposed to be from two replicated experiments. Okay, however, in reality, it's not that it sounds like trivial, because the optimal score for two experiment spectra may be dependent on the features or characteristics of the spectra, and as well as the peptide itself. So to devise a best optimal score to score two replicated experiment spectra from same peptide may not be as trivial as just using those common used vector similarity scores like cosine similarity. So as I said, there are two different approaches, spectral library search versus database search. And of course, database search has been used more frequently. Even though, as I mentioned, it seems like evaluation of the matching between two replicated experiment spectra is more straightforward. However, it's not as commonly used as the database searching, simply because there's not a good reference spectral library covering a large number of peptides supposed to be in the protein database. Roughly speaking, only a fifth of peptides from human protein has been reliably previously characterized and is collected in the reference spectral library like NIST libraries. So in that sense, if you just do a spectral library search, you can at most reliably identify about a fifth of the peptide in the in the sample. So of course, that's not satisfactory. So that's the reason we actually try to address two challenges here. So first is we ask if it's possible to develop a scoring scheme, somehow optimal scoring scheme, to more effectively differentiate between two replicate tandem spectra of identical peptide and the two spectra originated from different peptides, okay? Potentially similar peptides. Can we distinguish these two distributions? Second is, can we use the same scoring scheme to effectively differentiate between the pairs experimental spectra and predicted tandem mass spectra from identical peptide and those from distinct peptide? The second question arises because more recently there's many software has been developed based on deep learning to predict the tandem spectra from peptide, which has accomplished good accuracy. So if we can answer the second question, if we can develop a scoring function like can effectively distinguish not only two replicate experiment spectra, but also distinguish experiment spectra and predict spectra, then we can develop a unified approach to do not only spectral library search, but peptide database search based on predict spectra of those peptides in the spectral in the protein database. Okay, so I want to first summarize what we have been developing presenting this paper. So first, we develop a deep metric learning to embed tandem mass spectra of peptide into a latent space, and within the latent space, the cosine similarity can be effectively used to distinguish replicate spectra of identical peptide from spectra originating from distinct peptides. So essentially, we convert the metric learning problem into embedding problem. So we try to find embedding function based on deep neural network to convert spectra into the latent space so that the cosine similarity in the latent space is representing a best or somehow optimal score of the similarity measure of the original peptide. Original spectrum of the same peptide. And the second is, to answer the second question, we're trying to show, in fact, we can come up with a unified approach for spectral library search and database search using the predictor spectra based on the same scoring function. So just a reiteration of what we try to achieve use deep metric learning. So the challenge here is to distinguish the similarity measure from spectra of the same peptide and those spectra from different peptides. So if you just simply use cosine similarity, they are not completely separable as we show in the left figure. So the deep metric learning, you try to embed those spectra into a latent space so that the spectra from the same peptide are more separable in the latent space based on simple cosine similarity measure in the latent vector space than those from different peptides. Okay, that's what we try to achieve here. We're using, again, a deep neural network to achieve this. This is a brief overview of our model architecture. So first we use a temporal convolutional network to embed the spectra into a latent space. And in the meantime, we use actually a fully connected neural network to convert a peptide into another latent space. And then we use a loss function, try to train those two embedding network. So this loss function is comprised of two parts. First, we're trying to align these two latent space. So we basically want to make sure the spectra from the same peptide will be embedded into same latent space. The second part of our loss function is try to do a decoding of this latent space in order to predict the class of the spectral or peptide from the latent space. Here, each peptide in our training data represent a separate class. Okay, so if in training data you have like 70,000 different peptides, then there are 70,000 different classes. We're using AM softmax loss function to make sure that different the spectra from different peptide will be separated. So the additive marginal softmax is the extension of the softmax loss function that insert a margin in between two different classes, then make sure that different classes are separate even further. All right, so I want to point out there are 2 points. First, of course, you can use different embedding network architecture. Instead of using TCN, you can use transformer. Instead of use a fully connecting layer, you can use those commonly used peptide embedding network like ISM and so on. We're just there's no particular reason we choose this network structure, just because they are actually extension of our previous work. For example, the embedding spectral embedding is based on our embedding network used for our de novo sequencing algorithm PepNet. Another thing is that you may ask, why do we need to embed the peptide, not only embed the spectra together with the peptide? So we are trying, there are 2 advantages of this approach. First, we are trying to make sure that the embedding of the spectra essentially is correlated with the peptide where the spectra is coming from. Okay, so in other words, so we want to see that those spectra from similar peptide will be embedded into the latent space that are also close to each other. Secondly, we also want to make sure that the scoring function or the embedding itself, okay, we're only not only based on the characteristics of the spectra, but also the features from peptide sequence. So that's the reason we choose this approach for deep metric learning. So after we train those models, we can actually do 3 different approaches. Essentially, it's a unified approach for spectral library search and protein database search. For spectral library search, we simply embed the spectral, all the previously characterized experiment spectra in the spectral library into the latent space. And for any new data set come in, we just embed each experiment spectra into the same latent space and do a comparison in the latent space based on these embedding vectors. Okay, and of course, the cosine similarity will be used here to score the similarity between those latent space. Okay. Secondly, if we can also do a protein database search, here we just use our spectral prediction algorithm pretty full, but actually you can use any spectral prediction algorithm like ProSeed or any algorithm to predict all the spectra in the protein database, spectra of all the peptide in the protein database into experiment spectra. And can you use it you do the same thing as you search against spectral library, but in this case, you search against the predict spectrum instead of previously characterized experiment spectrum. All right, and you can even do a hybrid search. Okay, as we show, hybrid search actually achieve much better performance than simple database search. As from our result, in hybrid search, you can choose an experiment spectra. If it's including the spectral library, do the embedding using experiment spectra. But if a peptide is not including the spectral library, you can use predict spectra. And in the end, you get a hybrid or mixed library of latent vector embedded either from experiment spectra or a predict spectra. So some implementation detail I briefly mentioned. So we implement this in the Keras TensorFlow, and then we train it to train separate model for charge 2 and charge 3 spectra, which are most commonly observed in bottom-up proteomics. This was trained on about 1.5 million charge 2 spectra on about 70,000 unique peptide and about 1 million charge 3 spectra from around 50,000 unique peptide that collected from multiple spectral libraries. It takes about 12 hours using 8 cars on NVIDIA, and source code is released. If you're interested, you can try our code. And then we can do the inference when, just as I mentioned, you can do spectral library search, you can do database search, protein database search, and also do a hybrid search. The speed is around like the search, in our case, to search against a human database. Here is just for the embedding. If you measure the embedding, it takes about 1 millisecond per spectra to embed the input spectra into the latent space. And then we test this algorithm using 3 large scale experiments from human proteomics. Each contain like over 10 million to 20 million tandem spectra. So we first, before we actually really test the peptide or protein peptide identification result, we compare the similarity of the tandem spectra from replicate spectra from the identical peptide in the latent space versus in the input spectral space. The x-axis here represents the cosine similarity measured on the input spectra without embedding. And you can see for the true SSM, those are the replicate spectra from the same peptide. With the false SSM, you can see their cosine similarity score are not completely separated. So you can see there are large overlap around 2.7 even. But after embedding, if you measure the cosine similarity in the latent space, you can see the true SSM, basically from replicate spectra, are almost completely separated from the false in the y-axis, from completely separated from the false SSM. So that shows the embedding actually is effective to lead to a better scoring, cosine similarity scoring in the latent space. Then we test the improvement on the protein identification by spectral library search. So in this case, we compare with spectral ST, search against the NIST library for 3 data set. And I only show 1 data set here, but the other result you can see from our paper, they are very similar. So here, the blue ones are the identification number from unique peptide and the PSMs. PSM on the left, a unique peptide from right. And the red is the spectral encoder, our approach. I should mention here, spectral ST also use an empirical score. It's not a simple cosine similarity. Actually, their paper shows that their empirical score performs better, slightly better than the simple cosine similarity in the input space. But still, you can see SpecEncoder achieve a little better, actually can identify around 2% more PSMs and unique peptides across the data sets. In some better case, maybe I can achieve 3 to 4% more. So we can see that even here, we did not achieve a lot of improvement simply because the measurement of experiment spectrum may be not so hard. Now we actually try to compare the peptide identification using protein database search based on completely predict spectra versus a hybrid search where the embedding vector is the library of embedding comprised of either embedding vector from experiment spectral, if the peptide is including the spectral library, or a predict spectral if it's not in there. So here we compare against 2 baseline. One is the MSGF, one of the commonly used peptide identification algorithm, and the second is MSGF plus percolator, post-processing by percolator. So this red and the blue are these 2 baselines, and then the purple one here represents the result from the database search against a complete predict spectra. And we show that there are about 5 to 6% improvement on the unique peptide and the PSM level comparing to MSGF plus percolator on 1 data set again, but there are similar results we can achieve from other data set. And if you use hybrid search, you can achieve another 6% improvement. Okay, so this basically showed that not only our method can be used for search against the spectral library, but also can be used to search against the predicted spectrum. All right, and of course, if you combine the experiment spectrum and predict spectrum, you can achieve even better results. Okay, so a recap of what I just have talked about. So we developed a latent vector representation using a deep metric learning, and it offers a unified solution for spectral library search, protein database search, and the hybrid search, combine both approaches. Oh, I should mention all the previous results are based on the same FDR rate calculated using, based on 1% FDR. And the FDR calculated spectral library search were based on the same method used in Spectra ST, and the database search was used, also used a commonly used target decoy search approach. But I also want to mention that this performance can be further improved with more training data. So of course, and it can be easily extended to other charge spectra with fewer training data, of course, and also with PTM peptides. Finally, we think the latent vector implantation maybe even extend to de novo peptide sequencing if a decoder is added to the model to transform latent vector back to peptide sequence. All right, so just some acknowledgement of funding agencies. Thank you.
Hey, great talk, very
you.
interesting data. I was wondering, you showed that scatter plot of similarity in cosine space and similarity in latent space.
Right.
And those are spectra, you said, that belong to the same peptide.
Left, true SM are the replicate spectra.
Yeah.
The right side are the false ones. They are
Okay.
not from the same spectrum.
So, but so are these part of the training data set, or did you embed completely new
These
peptides?
are from actually testing data. They are not completely new because there
Okay.
could be some peptide overlapping between training and testing.
Ah, okay.
Yeah.
All right.
We
thanks.
did not, but they are only, I think, 10% to 20% overlapping.
Okay, thank you.
Sure.
Thank you for your presentation. I was wondering, maybe I missed it, but the type of instruments that was used for the training and the testing, is there a diversity there, or?
No, they are all HCD spectra.
All HCD, but
Yeah,
the instruments are?
From I think from either basically they are thermal instruments. They are, I think, two of the testing data are from QE and one is from Orbitrap.
Okay, so it's all Orbitrap based.
Right.
Okay, and the testing also.
Yes.
Okay, thank you.
Sure.